Batch and stream processing. I would say that the goal of data integration is to make sure that data ends up in the right form in all the right places. Doing so requires consuming inputs, transforming, joining, filtering, aggregating, training models, evaluating, and eventually writing to the appropriate outputs. Batch and stream processors are the tools for achieving this goal. The outputs of batch and stream processes are derived datasets such as search indexes, materialized views, recommendations to show to users, aggregate metrics, and so on. See the output of batch workflows on page 411 and uses of stream processing on page 465. As we saw in Chapter 10 and Chapter 11, batch and stream processing have a lot of principles in common, and the main fundamental difference is that stream processors operate on unbounded datasets whereas batch process inputs are of a known, finite size. There are also many detailed differences in the ways the processing engines are implemented, but these distinctions are beginning to blur. Spark performs stream processing on top of a batch processing engine by breaking the stream into microbatches, whereas Apache Flink performs batch processing on top of a stream processing engine. In principle, one type of processing can be emulated on top of the other, although the performance characteristics vary. For example, microbatching may perform poorly on hopping or sliding windows. Batch processing has a quite strong functional flavor even if the code is not written in a functional programming language. It encourages deterministic, pure functions whose output depends only on the input and which have no side effects other than the explicit outputs, treating inputs as immutable and outputs as append-only. Stream processing is similar, but it extends operators to allow managed, fault-tolerant state. See rebuilding state after a failure on page 478. The principle of deterministic functions with well-defined inputs and outputs is not only good for fault-tolerance. See idempotence on page 478, but also simplifies reasoning about the data flows in an organization. No matter whether the derived data is a search index, a statistical model, or a cache, it is helpful to think in terms of data pipelines that derive one thing from another, pushing state changes in one system through functional application code and applying the effects to derived systems. In principle, derived data systems could be maintained synchronously, just like a relational database updates secondary indexes synchronously within the same transaction as writes to the table being indexed. However, asynchrony is what makes systems based on event logs robust. It allows a fault in one part of the system to be contained locally, whereas distributed transactions abort if any one participant fails, so they tend to amplify failures by spreading them to the rest of the system. See limitations of distributed transactions on page 363. We saw in partitioning and secondary indexes on page 206 that secondary indexes often cross partition boundaries. A partition system with secondary indexes either needs to send writes to multiple partitions if the index is term partitioned or send reads to all partitions if the index is document partitioned. Such cross-partition communication is also most reliable and scalable if the index is maintained asynchronously. See also multi-partition data processing on page 514. Reprocessing data for application evolution. When maintaining derived data, batch and stream processing are both useful. Stream processing allows changes in the input to be reflected in derived views with low delay, whereas batch processing allows large amounts of accumulated historical data to be reprocessed in order to derive new views onto an existing dataset. In particular, reprocessing existing data provides a good mechanism for maintaining a system, evolving it to support new features and changed requirements. See Chapter 4. Without reprocessing, schema evolution is limited to simple changes like adding a new optional field to a record or adding a new type of record. This is the case both in a schema on write and in a schema on read context. See schema flexibility in the document model on page 39. On the other hand, with reprocessing it is possible to restructure a dataset into a completely different model in order to better serve new requirements. Schema migrations on railways. Large-scale schema migrations occur in non-computer systems as well. For example, in the early days of railway building in 19th century England there were various competing standards for the gauge the distance between the two rails. Trains built for one gauge couldn't run on tracks of another gauge, which restricted the possible interconnections in the train network. After a single standard gauge was finally decided upon in 1846, tracks with other gauges had to be converted. But how do you do this without shutting down the train line for months or years? The solution is to first convert the track to dual gauge or mixed gauge by adding a third rail. This conversion can be done gradually, and when it is done, trains of both gauges can run on the line, using two of the three rails. Eventually, Once all trains have been converted to the standard gauge, the rail providing the non-standard gauge can be removed, reprocessing the existing tracks in this way, and allowing the old and new versions to exist side by side, makes it possible to change the gauge gradually over the course of years. Nevertheless, it is an expensive undertaking, which is why non-standard gauges still exist today. For example, the BART system in the San Francisco Bay Area uses a different gauge from the majority of the U.S. Derived views allow gradual evolution. If you want to restructure a dataset, you do not need to perform the migration as a sudden switch. Instead, you can maintain the old schema and the new schema side by side as two independently derived views onto the same underlying data. You can then start shifting a small number of users to the new view in order to test its performance and find any bugs, while most users continue to be routed to the old view. Gradually, you can increase the proportion of users accessing the new view, and eventually you can drop the old view. The beauty of such a gradual migration is that every stage of the process is easily reversible if something goes wrong. You always have a working system to go back to. By reducing the risk of irreversible damage, you can be more confident about going ahead, and thus move faster to improve your system. If batch processing is used to reprocess historical data, and stream processing is used to process recent updates, then how do you combine the two? The Lambda architecture is a proposal in this area that has gained a lot of attention. The core idea of the Lambda architecture is that incoming data should be recorded by appending immutable events to an always growing dataset, similarly to event sourcing. See event sourcing on page 457. From these events, read-optimized views are derived. The Lambda architecture proposes running two different systems in parallel: a batch processing system such as Hadoop MapReduce, and a separate stream processing system such as Storm. In the Lambda approach, the stream processor consumes the events and quickly produces an approximate update to the view. The batch processor later consumes the same set of events and produces a corrected version of the derived view. The reasoning behind this design is that batch processing is simpler and thus less prone to bugs, while stream processors are thought to be less reliable and harder to make fault-tolerant. See fault tolerance on page 476. Moreover, the stream process can use fast approximate algorithms while the batch process uses slower exact algorithms. The Lambda architecture was an influential idea that shaped the design of data systems for the better, particularly by popularizing the principle of deriving views onto streams of immutable events and reprocessing events when needed. However, I also think that it has a number of practical problems. Having to maintain the same logic to run both in a batch and in a stream processing framework is significant additional effort. Although libraries such as Hummingbird provide an abstraction for computations that can be run in either a batch or a streaming context, the operational complexity of debugging, tuning, and maintaining two different systems remains. Since the stream pipeline and the batch pipeline produce separate outputs, they need to be merged in order to respond to user requests. This merge is fairly easy if the computation is a simple aggregation over a tumbling window, but it becomes significantly harder if the view is derived using more complex operations such as joins and sessionization, or if the output is not a time series. Although it is great to have the ability to reprocess the entire historical dataset, doing so frequently is expensive on large datasets. Thus, the batch pipeline often needs to be set up to process incremental batches, for example an hour's worth of data at the end of every hour rather than reprocessing everything. This raises the problems discussed in reasoning about time on page 468, such as handling stragglers and handling windows that cross boundaries between batches. Incrementalizing a batch computation adds complexity, making it more akin to the streaming layer, which runs counter to the goal of keeping the batch layer as simple as possible. Unifying batch and stream processing. More recent work has enabled the benefits of the Lambda architecture to be enjoyed without its downsides, by allowing both batch computations reprocessing historical data and stream computations processing events as they arrive to be implemented in the same system. Unifying batch and stream processing in one system requires the following features, which are becoming increasingly widely available: the ability to replay historical events through the same processing engine that handles the stream of recent events. For example, log-based message brokers have the ability to replay messages. See replaying old messages on page 451, and some stream processors can read input from a distributed file system like HDFS. Exactly one semantics for stream processors, that is, ensuring that the output is the same as if no faults had occurred, even if faults did in fact occur. See fault tolerance on page 476. Like with batch processing, This requires discarding the partial output of any failed tasks. Tools for windowing by event time, not by processing time, since processing time is meaningless when reprocessing historical events. See reasoning about time on page 468. For example, Apache Beam provides an API for expressing such computations, which can then be run using Apache Flink or Google Cloud Dataflow.